Thanks a lot for the invitation. I'm really happy to talk here, and so far it was super interesting. And I want to tell you about explainable machine learning and how we can use it in the agriculture and environmental sciences. And actually, I work in digital agriculture, so I work a lot with UAV images, but also satellite images. So you will see all kind of images in my talk. But all methods I will show you are also applicable to satellite images. Okay, let's start with a typical example. So when we see such a situation, we have a typical question. For example, what is on the field, or what is the yield in this area, or what will this plant look like tomorrow? These are the typical what questions. And as we heard already, one of the most commonly used tasks in remote sending is land cover classification, and here we deal with imbalance data and in this case sparse labeled data, and so here we can ask what is the land cover. But I want to go beyond these questions today, and I want to ask why does a plant look like this, or why does the algorithm perform poorly here, or how did my algorithm come to a specific result? And we can answer this question with explainable machine learning. And if we think about explainable machine learning, we can think about three core elements. And one element is transparency. Transparency is when you think about, you think about the different ingredients of a machine learning model. For example, the model components, or even the motivation why a specific model was used. Then we can, also transparency is normally not a problem because we have access to a model, right? So we can even write down the equation. The problem is that deep neural networks are so complex, they are not understandable to us. And this is where interpretability comes into play. Here we present properties of a machine learning model in understandable terms to human. An easy example is you visualize the importance of the input features which are relevant for a specific decision. And then there's explainability. Explainability is when you combine these interpretable entities with domain knowledge, and in the best case with an analysis goal. If you go to the literature, there's no common understanding or no unique definition of interpretability and explainability, but the reason why my co-authors and I want to distinguish it, especially for scientific data, is the explanation depends on the use case. So you can have one interpretation, but you can have multiple explanations depending on the added domain knowledge, and they can all be correct. So it's good to distinguish between what does not change, so the interpretation, and what can change, the explanation. And if you think about it more deeply, there's a connection to causation. So causation means that an output is the result of occurrence of a specific input. So the input is the cause and the effect is the output. And on the other side, you have correlation. Correlation measures the relationship between the input and the output, but it does not imply causation. So to give you an example, it rains, that means the plants will grow, and it will also mean that I will use an umbrella. But it does not mean that when I use an umbrella that the plants will grow. And very often, not always, very often, machine learning models model exactly this. They model the correlation, not necessarily the causation. And this is what we need to take into account when we apply explainable machine learning, because also the interpretation tools generally build on this correlation. So we need to take care about the confirmation bias. Confirmation bias, we have an underlying tendency to search for explanations which are in line with our existing knowledge. So we might think we found something in our data because we really want to see it, but actually it was not the case. So this is nothing bad, but we need to keep this in mind when we use explainable machine learning tools. And I want to structure my talks into three parts and showing you different applications where my team and I used explainable machine learning. And I want to structure the talk into reasons to seek explanations. So first one is to justify decisions and improve models. We can enhance control, and we can discover knowledge. So let's start with the first application. So one project I have on my team is the optimization of cauliflower cultivation. So we have a look at the development and the growth, and especially the harvest readiness of cauliflower. And this is a complicated topic. At the moment, cauliflower is still harvested manually based on spot checks. So you go there to the field, you grab into the plant, and then you feel it, and if it has the right size, you extrapolate it, and then it's harvested. The problem is there's an irregular development. Even if you have the plants planted right next to each other, they can develop quite differently. And so what we did, we want to support the farmer, the farmer's decision making with machine learning and UAV data. And we have, for this, we acquired geo-reference data over time. We use for this the ground control points. We use a neural network in an early growth stage, so that we could extract the plants over time, so we can track them over time and estimate the size, for example. Starting at a specific point in time, then we learned a neural network and learned it for if the head is, if the plant is ready for harvest or not. And you can already see you're not seeing the cauliflower, so it's totally covered with leaves. It's not how you see it in the supermarket. You can actually not see it, otherwise it would turn yellow, and then you cannot sell it anymore. So this is how it looks on the field. This neural network was able to reach an accuracy of 73%, which is okay, and which was good because the farmer told us that's not possible at all. So we were already quite happy, but we wanted to know, is the decision really based on the right reasons? And for this, we used two different, very easy tools. One is occlusion sensitivity maps. Occlusion sensitivity maps is here you assume you have a fixed model. In our case, the model that is able to classify between ready for harvest or not, and you get a specific score for a class, right? And now you cover up the input image systematically with a small patch, and you see how the score changes. This difference in the score is the attribution, and in this case, it's the sensitivity. And it's an indicator on how important this specific part of the image was for the decision, for the classification. Another tool we use is gradient-weighted class activation maps, GradCam, very commonly used. Also in remote sensing, I saw a lot of works. This is specifically designed for convolutional neural networks. And here you have activation maps. In this case, in the very last convolutional layer, and these activation maps are weighted by the backpropagated gradients from the specific class, and they are globally average pooled together and summed together, and in this case, you also get such an attribution map. And in our case, we also tested a few other tools, for example, Lime. Lime works very well for any other data, but not agriculture data. And the reason is it's based on surrogate modeling and superpixels. But it's so hard to get here already a good superpixel segmentation that it was just not working for us. So we sticked, in this case, actually with GradCam, and now what we did is we used a lot of training images, extracted the saliency maps from it, and then we performed spectral clustering. This is a nonlinear clustering technique. And we derived, in this case, 8 cluster centers. And you can already see most of the clusters point towards the middle, which is good because this is where the plant is. But here we have a cluster center or a cluster which looks at the corners. And you can already imagine might not be good. And if you connect it to the classification accuracy, you can also see it. So what you see here is these are the 8 cluster centers, and this is the fraction of the true, or the correct classification and the wrong classification. So wrong is in red, and correct is in blue. And cluster 3, 5, and 8 contains mainly correct classification, but there's one cluster that contains mainly incorrect classification. So if you have now a test image and you get the saliency map and it falls into cluster 1, you know this is not correct. You should not trust the result. So you can say, okay, we cannot make a decision about it. In our case, we actually could switch the decision, and the accuracy went from 73 to 85%. I would generally recommend just say you cannot decide on it. But you can clearly see that you can use heat maps or the saliency maps to increase the trust in the results, to get more insights into the decision process of the model, and this was clearly a wrong decision process in the model. Right, but we have time series data, and so far I showed you just some results about single images. And if you think about UAV overflights, it's a very tedious process. So the drone pilot needs to have time, very important factor. The weather needs to be good, and you need a lot of time. And so we thought, can we make use of explainable machine learning to see which overflight dates are actually not important, so we can use this insight in the next season and just to get rid of a few overflights. And for this, we use Shapley values. And I want to briefly show you the principle of Shapley values because I think it's a really nice theory behind it. So Shapley values originated from game theory. And in game theory, we have players, and they play in a coalition. That means it's a joint effort. They play together a game, and then you have an overall payout. If we now use this for our application, we have a set of images. These images are the players in our coalition. The prediction task is our game, and then we have an output, and this is the overall payout. And Shapley values now give you the contribution or the payout of each player, that means each image, based on the contribution with the mean prediction being the reference. So you have a lot of prediction over the whole data set, and the mean prediction is now our reference data. And now you want to see what is each image in the time series contributing to a deviation from this mean prediction. So let me briefly explain this to you, how it's actually computed. So you have a time series, and each image in the time series is one player. And let's now assume you want to compute the contribution of the gray player. What you analyze is the contribution of the gray player to all coalitions. So if the gray player plays with all other players, if it plays alone, if it plays only with the yellow player or only with the blue player. And this is afterwards, all these single contributions are weighted and averaged. So let's have a look at the first one, how the contribution is actually computed. So you have once the prediction without the gray player and with the gray player. The problem is now you have a machine learning model. You cannot just take out something because otherwise you would need to retrain your model. So what to do? You can use marginalization. Marginalization means you just use typical values from your data set. You compute all the predictions with these different values, and then you average them. That means you average or you marginalize out the effect of the gray player. You take this as for the prediction without a gray player and compare it then to the actual constellation. You do this for all the coalition, weighted and average, and then you have your Shapley values. So for our example now, so here on the left side, you can see our model. So we have time series data. We have a spatial encoding. Of course, we have images. And then we have a temporal encoding. Temporal encoding is important because not all plants are planted at the same date, on the same day. So we encode the day after planting. And also our time series data is not equidistant. That's the difference to satellite images. So we need to take care of these time steps. And this is a binary classifier. And this image does not, okay, I will tell you what you should see. In this, so what you can see here is actually the Shapley value and the overflight day. So what you see is the deviation from the average prediction. The average prediction of a classification task is guessing. So what you see here is all the Shapley values from all these images from a specific point in time and how they deviate from guessing. And you can see that here's the day 50 overflight. It doesn't really contribute. So you can take out this time point. And we compared it. And this is the results we obtained. So what you can see is the overall accuracy and the balanced class accuracy here on this axis, and the time series length. Yellow is just a reference. When you take just a single point in time, this is what I showed you in the very beginning. So when you only have one single image. And in blue is when you have a time series starting from the very first day, taking the next day, again and again, so overflight day, not next day. And what you can see is more is not better. So it can happen that you take or you make a time series longer and it confuses the model, or the data is noisy. So it's not always good to just take all the data you have. And in gray, you can see when we have, or when we design our time series based on the contribution, what I showed you before, where we selected only specific points in time with the Shapley values. And this is exactly the model where we reach the highest accuracy. And this we can now use for the next season to plan our overflights in a better way. Right. So in the second part, I want to briefly show you how we can how we can use interpretability and interpretation for generative modeling. So what is advantage in agriculture is when you know how a plant will develop in the future, or more generally, how a plant will look, or what the plant will look at a specific point in time, and in the best case, based on factors of variation. Factors of variation are, for example, some environmental factors like watering. And we designed a generative model for this, and we got a data-driven image-based growth model, conditional on the factors of variation and an early growth stage. An early growth stage because you do not want only to have nice-looking images, you really want to have this specific plant, and you want to see how it will develop. And as I said, we trained, in our case, a generative adversarial network. You can also use diffusion models. They also work. We tested it, but here we have the more results to show. And so we trained a network, a generative model. And these videos are generated based on a few input images. So now we can see how the plant will most likely develop over time, in between the time points and also a bit into the future. But this is Arabidopsis thaliana, which is the MNIST of the plant scientists. So this was just for testing. But we had an actual problem, an actual application, which is our mixed cropping experiment in Bonn. Mixed cropping is a promising way towards sustainable agriculture. So here we plant two crops together, in our case, faba bean and spring wheat. And if we do this, if we plant them together, you can increase the yield and at the same time reduce the chemicals. But it's not clear what is a good fraction. And you cannot test everything in the field. It's impossible. And what we have is we have autophotos over time, and we have further information about the seed number, the biomass, the weight, the height, and so on. And we designed a generative model where interpretability was the key to be actually successful. So what we did is, so here is our generator, and the model is based on an early growth stage and a later growth stage. And we have a low-dimensional disentangled interpretable latent space. We started from our factors of variation. So the seed number, or it was just a table of numbers. We embedded it into a feature space, which is where a dimension is related to the biomass, another dimension is related to the seed number. And we embedded the later growth stage exactly to the same space using the Kullback-Leibler divergence. So the thing is now we can query in growth stage or later growth stage now with changed factors of variation. And this is only possible if it's interpretable. Otherwise, you have no idea what is actually going on in this space. And this was the key to change the environmental factors, and just to show you one example, this is the input image from our field. This is the real appearance of faba bean and springweed, and this is what we measured in the field. And now we change the factors of variation. So for example, in the very right image, we set all the faba bean factors of variation, like the seed number and the mean height, to 0. And in the generated image, there's no faba bean. And it's the same for the second image from right. There we set all the factors of variation for springweed to 0, and it's actually only faba bean in the image. And this is, why is this useful? Because now this can be used at artificial sensor data. You can treat it like as you would acquire it in the field, and so you can generate hypotheses how plants will grow together. Okay, so, but let me go to the last example, which is one of my favorite topics right now on my team. Here, we want to do a worldwide mapping of wilderness. The problem is there's no technical definition of wilderness. There are some definitions out there, for example, from the European Commission, and it says a wilderness is composed of native habitats and species and large enough for the effective ecological functioning of natural processes. It says large enough and natural and such things, but this is nothing we can use for machine learning, and there's no defined land cover class for wilderness, so we don't know how we can use it for mapping. And we used explainable machine learning to get more insights about this vaguely defined land cover class. And we used a study site in Fennoscandia, which is Norway, Sweden, and Finland, and what we are good in is we can define extremes. So we can clearly say, okay, this is a wide area, so no human influence, somewhere I would not go, I cannot go, something like this. And what is not wide, like anthropogenic areas. So we use the world database on protected areas as a proxy for wilderness, and the anthropogenic areas as a proxy for non-wilderness. And we used Sentinel-2 data, and our first thought was from this area, yeah, forest is a typical indicator for wilderness, but as you can see, it's not. It's not that easy. Everything's green, and there's a lot of forest everywhere. So let's let the network do the job and tell us more about what is wilderness. And we designed a specific network for it called JungleNet. JungleNet is a combination of a UNet and a convolutional neural network, a decision network. So the first part here is a UNet, and the second part is a convolutional neural network. The output of the UNet, that's the important point, has the same resolution as the input. So if you go there and you analyze the activation maps, or if you perform GradCam exactly to this layer, you always can operate in full resolution. That's why we designed the network in this specific way. The network is actually a regression network because, as I said, we only define the extremes. That means we somehow need to define something in between in a controlled way. What we did is we used cut mix. Cut mix means you have an image patch, you cut out from one class a specific part of the image and you patch in the other class. So we have a wilderness fraction and we can learn the network exactly with this in a controlled way. And then we had a look exactly at these activation maps here. And we used this for, we had 19,000 training samples and we extracted actually 3 activation maps for each of the samples. So each pixel is 3-dimensional and you can put it in a so-called activation space where each dimension belongs to one activation map. And you can already see it's not random. There's already some structure in it. And now we used the idea of occlusion sensitivity, but we did it in the activation space. That means we defined a cube, and systematically we moved the cube to this activation space, and we covered up, or we set all the activations in the cube to 0. And in this way, you can actually switch off some information in the network. That's not possible in the input, but in the activation space, you just set it to 0. And then you have a look at how the score changes, and if you do this, you get actually from this activation space to sensitivity information. And in green, highlighted, this are all activations which are sensitive towards wilderness. In purple, this is sensitive towards non-wilderness, and in beige, you get everything in between. So even if you cover up something, it will not change the score. And the nice thing now is, or a crucial thing, what I forgot to say, we did also a harmonization. Harmonization means it's a bit noisy, so we did some smoothing, and also you can use this now as a lookup table. So it doesn't matter how big your image is, you can feed it into the network and use this lookup table, and you get harmonized saliency maps. So there's no difference between when you feed in they independently, so you can stitch them together afterwards. So these were actually 4 different images. And what you can see here, this is from a site in Finland. In green is an area with patterns associated with wilderness. These are wetlands. And here you have a purple area which is associated to non-wilderness. And we were first wondering why. It looks like a dense forest, but if you look really, really closely, it's artificially created forest. So you have man-made structures. It's really, you see the pattern in there. So the algorithm actually identified that this is not connected to some wide area, but it's man-made. And such approaches can help us now to get more insights into what this land cover classes actually looks like. And this is work in progress, and I want to show you some more direction in this way. So this is the activation space occlusion sensitivity approach, what I showed you before, but you can also use GradCam in this layer, right? And GradCam is normally characterized by these blobby saliency maps, but if you use it with this specific network, you get a pixel-wise attribution map, and you can analyze it. At the moment, we look in how how we can make use of the difference between, or the different shades in there, and if it has a meaning. You can also use it for weakly supervised learning. So imagine now you use a similar network, and you do not have a wilderness fraction score, a regression network, but you have a scene classification network. And scene classification is when you just say, okay, I know in this scene there's forest, there's water, there's some land cover class. And if you train the network with it, and then you can, for example, if you use GradCam, you can backpropagate the gradient and compute the attribution map for each land cover class. And if you then use or look at the maximum, you get an indicator in what a specific activation is, or to which land cover class a specific activation is connected to. And you can see this in this space here. So we never learned a semantic segmentation network, but this is a way how you can get semantic information pixel-wise, and the network figured it out on its own. And here, for example, this is an image from the DFC data set. You have here the ground truth. And this is the semantic segmentation map we obtained from GradCam. Also work in progress, but promising way, I would say. Right, I have two slides left. One different approach I want to present here is you can also use generative models to get attribution maps. So for example, you can use an image of protected natural area, which is a proxy for wilderness, and you get a score, for example, from 0.9, right, from an arbitrary network. And then you can use a generative model, which, for example, increases the score, so it maximizes all the patterns in the image. And on the other side, you have a generative model that minimizes the patterns. That means it minimizes the score for the specific class. And if you now take the difference between these two images, it will highlight exactly the patterns that were important for this wilderness. And we compared it also with different approaches. Here you can see the original image. This is deep lift, also another interpretation tool, occlusion sensitivity map, and GradCam. And this is ours. And you can already see that we have a very detailed indication which parts in the satellite image are actually responsible or show wilderness patterns. And if you compare it now to a land cover class, so external domain knowledge, you can see that it's mainly connected to wetlands. Right, so very last slide. You already heard about data-centric machine learning a lot, especially from Manil this morning. And I want to emphasize this a bit more. So currently, there's a big movement about data-centric machine learning. And a lot of research in machine learning is model-centric. That means we focus on model parameters, on hyperparameters, loss functions, so on. That's all okay, but first of all, this learning paradigm oftentimes treats the data as a static benchmark. So it stays that it is, and we do not really care about it. And moreover, most of our models and methods already saturate on this benchmark. That's why some colleagues and we think we should, there's a need to shift the focus to a complementary learning paradigm, the data-centric machine learning, which is about systematic, automatic, and algorithmic determination and the utilization of a rich and high-quality data set, and also rigorous evaluation. This was also mentioned already yesterday. And so we need data that in the model which optimally performs on the data set for the intended task. And an important part is this feedback loop. So you have the machine learning cycle and the data-centric machine learning cycle. There you have a feedback loop. So you focus on the model, and the model is then used, for example, to optimize the data, and then the optimized data is again used to improve the model. And explainable machine learning is actually a puzzle piece in it, because explainable machine learning can help us to point us to data points which are actually not really suitable for our model and so on. Yeah, so from my point of view, very promising direction. I would recommend to go in this direction. And with this, thank you very much for your attention, and I'm happy to take questions.
Yeah, thank you, Ribana. Yeah, very nice presentation. 3 very impressive use cases for explainable AI in agricultural sciences. And yeah, now I would ask the audience if there's any questions to this talk, to the speaker. In the back. Very back, yeah, at the tables.
Walk all the way over here. Thank you for your talk. I think it seems, okay, so most of the time when people talk about explainable AI, they're talking about it in terms of building trust for end users in the model or explaining what's happening. But it seems like most of the use cases, maybe all that you had, were actually ways to post-process or minimize errors in the model before it even gets to the end user. Do you think that there are uses in actually explaining things to end users, or are most of the uses for model development or improving robustness of models?
Right, it's actually, I think this is the #1 reason which is mentioned in papers, but I don't see this as a #1 reason. I totally agree. I mainly use it to get new insights from data, which is from a clear research perspective. For example, what we did for the cauliflower, I also did for whale flukes. So we actually, when you do whale monitoring, tourists take photos, right? And so then these photos are uploaded to a database and then automatically analyzed, so that you can track the spatial migration of these whales and to see if something is wrong. So here I would see, for example, if you would upload the photo and you have a model running and you could guess an additional kind of uncertainty measure about the quality of the result. So maybe it could reject it from the database and not use for further analysis. So there I would see a use case, but this is more the trust in a way that you use it as a reliability measure. But I can, to be honest, I cannot see that a farmer is really gets more trust if I show it.
Right.
This.
Yeah, I just always wonder, like, are we talking about the wrong thing in
Yeah.
explainable AI and interpretable? And I don't know, do people really trust things more when they see an explanation? It seems like not. Like, people use ChatGPT
No.
and definitely don't understand how it's getting to those answers.
That's true. Actually, it would be nice to have three components: the actual result, then an uncertainty, and some kind of explanation which is understandable by whoever user. And this also differs. So we are doing heat mapping. Maybe others don't like it. They want a number.
Right.
Yeah.
Is there another question? Yeah.
Thank you. Yeah, I was just thinking maybe it also depends. I thought that was a very good question. It also depends on whether the end users can actually distinguish a correct from a wrong result, right? I think with LLMs, you can judge whether what you got is fit. But if you look at the crops, you might not know was the scenario successful or not.
Exactly. That's why this is actually also one reason why I always try to distinguish between the interpretation and the explanation, because the explanation is, we cannot really say something as a researcher because it so depends on where it is used, what the end user is, but we can provide methods for good interpretation. So for this Shapley values or the saliency maps and so on, and but then we need to think about how can we actually use it from there on, and this is also the deployment step. But yeah, it's challenging, I would say. Yeah.
Is there another question? All right. Then I also have another question. Actually, since explainable methods came up, I had the feeling there was always a strong debate how useful they actually are. So there's different perspective, I'd say, in the deep learning community. We've seen some very useful use cases, benefits. Did you encounter limitations in your research line? And yeah, what would be the risks or limitations of explainable AI, especially in agriculture?
Yes, so the risk is exactly the confirmation bias, and that we wrong, or that we get something wrong from the interpretation or explanation in the end. A limitation, what I see, is so most of the methods developed are developed for images where you have a nice shaped object in the middle of the image, and then the dog and cat, and that's fine. But it's not the case for the images we work with. And what I realized is, so normally you cannot expect that the saliency map or this hotspot covers up the whole object. That's what we try to circumvent with all these different approaches with the wilderness example. I have no good solution for it. We still need to think a lot about how to evaluate in the end. There are good papers coming up. There's a good line of research. But currently, I always start my talk with, it's good, but you need to keep in mind this, and this, and this, and be careful with it.
I see. So maybe also a good future research direction to develop maybe explainable AI for remote sensing specific tasks.
Good direction.